We're going to be looking at how to balance reaction equations, and you should have these examples here to follow along with on your own already. I'll be doing one of these per slide, and I wrote over here, or included over here, a place for you to write the reaction type, but I'm going to just do it kind of loose and free on the screen here. And so we're going to go through how to identify a reaction as well as how to balance it. So the first thing here is on this particular reaction, I see that we have a plus sign on the reactant side and no signs over here on the product side. And that tells me that this is a synthesis reaction. Although you can abbreviate it however you'd like, as long as I can tell it apart from the others. I recommend synth like I just did there. Then from there, we need to balance the two sides of the equation. So over here, I notice that we have two hydrogens, and over here, two hydrogens. So my hydrogens are good to go. And then here we have two oxygens, and over here, I only have one oxygen. So you might be tempted to say, oh, well, can't we just go to there? And the answer is no, not at all. You cannot, absolutely cannot change a chemical formula. It's not allowed because this is a reaction showing the burning of hydrogen and oxygen together to produce water. If you change this to H2O2, it is no longer water, it is hydrogen peroxide. So we cannot ever change chemical formulas. We've went through previously in the bonding topics how to determine a chemical formula, how to figure out what the proper formula is from the name and from the charges or the number of valence electrons, and be able to figure out the actual formula. But once you have a formula, you cannot change the formula. The only way that you can do this is by inserting coefficients. So I need to insert a number in front here. So I have two oxygens here, and I want two over here. So the simplest thing to do then is to multiply that by 2. Well, great, my oxygens are balanced. And you might say, okay, now I'm done. But you're not, because by putting this 2 coefficient here, we've now changed the number of hydrogens. We now have 2 times 2, and keep in mind these are coefficients, they are distributive, which means they are multiplicative, that is, you multiply them. So we have 2 times 2 hydrogens, and now we have 4 hydrogens here, so we need 4 hydrogens on the other side. Well, fortunately, that's a simple fix here. It's just another 2 there, and here we can double check now. 2 times 2 hydrogens, 4 hydrogens on the reactants, and 2 times 2, 4 hydrogens on the products. We have invisible 1 here, if you prefer. We won't normally write it in there, but invisible 1 times 2, and 2 times invisible 1. 2 oxygens and 2 oxygens. So then this reaction equation is balanced. It just gets too crowded if we write the ones, so we don't have them. If you want to put them in there temporarily to help you, that's fine, but make sure you erase them when you're done. We obviously have at least one of these, or we want to write O2 there. But that's the basics of how to balance. We're going to do an example of how to balance with each type of reaction equation here. So skipping forward, we now have this one. Again, the first thing to do is to try to identify the type of reaction. So I notice here, no plus sign on the reactants, but there is a plus sign on the products. And from your notes, you can see that this one is what we would call a decomposition, or decomp for short. From there, again, we need to balance. So I have 1 nitrogen here and 2 over here. So I'm going to need to end up multiplying this by a 2 here. And now that gives me 2 nitrogens on the reactants and 2 nitrogens on the products. And now I've really thrown off my iodines. I have 2 times 3, that's 6 iodines over here. So I need 6 over here. And you end up with a 3 coefficient there. One thing I will point out that happens quite frequently is that when we are doing balancing, you often end up with a coefficient subscript combination here matching over there. They end up being the opposite of one another. That is, we have a 2 coefficient over here and a 3 subscript, and over here we have a 3 coefficient and a 2 subscript. And that happens because of the way that math works. That is one of the properties that you learned in algebra at some point, that A times B is equal to B times A. And so it works as a shortcut, and you'll see that quite frequently. Last thing as well, we should always check. when we're done, especially because sometimes when you balance one, it throws off the other. So 2 nitrogens and 2 nitrogens, 6 iodines and 6 iodines. We're good to go. For our next reaction type here, I have a plus sign on both sides of the reaction. That means that this is one of the 2 replacement reactions, most likely. It could be a combustion, but I don't see any oxygens alone or water or carbon dioxide in there, so this is a replacement reaction. The problem is we have to identify which of the 2 types of replacement reaction it is. So the way we do that is over here, I notice we have something alone, and we have a binary or higher compound, something alone, and a binary or higher compound. When that is the case, where you have something alone on both sides, that thing is alone and is called a single replacement, or SR for short. I will point out as well with single replacements that what's going on here is that the aluminum is coming in here and replacing the copper, and the copper is just leaving. And so the copper is not really replacing the aluminum because the aluminum wasn't part of something else. And so we have just one thing taking the place of another thing, and that's what makes it a single replacement reaction. From there, we need to balance this one. So looking, I see I have 1 aluminum and 1 aluminum. They're good. 1 copper and 1 copper. They're good. And then I have 2 nitrogens and 6 oxygens. And you can balance it that way, balancing individual nitrogens and oxygens. But when you have parentheses on both sides of the reaction equation surrounding the same thing, that is, we have an NO3 and an NO3 here, we can balance the NO3s instead. You could think of the NO3 as X, and then we have X2 on this side, we have X2 on this side, and X3 on this side. That works. I personally like to just leave it as the nitrate, though, and just try to balance the nitrates out. So I have 2 nitrates here on the reactant side, 3 nitrates on the product side. So that says to me that I'm going to need a 3 here and a 2 here to balance those out. Well, that gives me 3 times 2, that's 6 nitrates, and 2 times 3, that's 6 nitrates, so my nitrates are good. But this, again, is a situation where once we've balanced one thing, we have to go back and check everything else because we've screwed up everything that was balanced before. So my aluminums were good before, but now they're not. I have 1 aluminum here and 2 over here, so that's going to take a 2 coefficient there. And then on my coppers, I have a 3 coppers here and only 1 there, so that's going to take a 3 here. And now we have 2 aluminums, 3 coppers, 3 times 2, 6 nitrates, and 2 times 3, 6 nitrates. And so everything on both sides is balanced, and you'll notice that it does take a coefficient in front of each of these this time. The others we had invisible ones. I will also point out here while I'm thinking about it that you can have reactions that are balanced already that take no coefficients to balance them out. They just happen to be balanced to begin with. This next one here is probably the toughest example I have, but I have it here to show you a trick. So the first thing is to identify the type of reaction always, so we have a plus sign on both sides, and you could probably take a guess, since we've done a single replacement already, that this one's going to come out to be the double replacement. But how do we know that? Well, again, the plus sign on both sides tells us that this is definitely a replacement reaction. But from there, we have to identify whether anything's alone. And over here, I have a binary or higher, that is 2 or more things bonded together. Binary or higher, 2 or more things bonded together. Binary or higher, 2 or more things bonded together. Binary, in this case, this one is actually binary, 2 separate things, even though there's 3 atoms there, 2 separate elements, making it binary. And so we have binary or higher in all of these places. This one is going to be a double replacement reaction, or abbreviated just a DR there. And what is going on in replacement again is here we have the phosphate coming in here and taking the place of the hydroxide, and the hydroxide coming over here and taking the place of the phosphate. And so we have 2 things taking the place of each other, and they're taking the place of each other because they're bonded to something else. Whereas in the single replacement reaction, the aluminum took the place of the copper, but the copper didn't replace the aluminum because the aluminum wasn't attached to anything. So that's a double replacement reaction. And now we need to balance this thing. As I said, this one's a bit of a doozy here, because I have H's there and H's there, and we could start to balance it out, and we could get there. But one thing I want to point out is that this one here happens to be an acid-base reaction. Now, we don't cover those specifically in here, but they do come up as examples sometimes. But we have a hydrogen compound and a hydroxide compound. It turns out hydrogen compounds are acids and hydroxide compounds are bases. And acid-base reactions always produce a salt and water. And so because of that, there's a trick that you can use when it comes to balancing these things. And that is, recall on the last slide, I talked about balancing the nitrates rather than balancing the individual N's and O's. We can do the same thing here. If we treat water, instead of as H2O, we treat it as HOH. And then we try to balance those pieces. So what I see here is 3 hydrogens, and so then I'm going to need 3 hydrogens here. Yes, 3 times 2 is 6, but I'm balancing the HOH, and I'm pretending that the OH here is its own thing. So I have 3 H's. Then I have 1 phosphate and 2 phosphates, so I'm going to have to put a 2 coefficient in front of here. That's screwed up my H's now, so I'm going to go ahead and fix that right now. So we have 2 phosphates, 2 phosphates. We now have 2 times 3, that's 6 hydrogens, so that means we're going to need 6 hydrogens here. We have 1 calcium and 3 calciums on the reactants versus product, so I'm going to need to put a 3 coefficient in front of the calcium on the reactant side here. And then that gives me 3 times 2, that's 6 hydroxides, and look, we have 6 hydroxides already. So let's double check everything. 6 hydrogens, 6 hydrogens, 2 phosphates, 2 phosphates, 3 calciums and 3 calciums, 3 times 2, 6 hydroxides and 6 hydroxides were balanced. If you wanted to go through and check individual atoms, we certainly can do that. So if we want to check the total number of hydrogens, for example, we have 2 times 3 hydrogens here, that's 6 hydrogens, and 3 times 2 hydrogens there, that's another 6 hydrogens. We should have 12 hydrogens total on the reactant side. And so then over here on the product side, we have 6 times 2, that's 12 hydrogens. And so again, it does work out. It's just a little bit trickier, and you end up getting into some steep coefficients sometimes with acid-base reactions, and especially with our last type of reaction. Now, if you've been following along with your older notes, you're going to know exactly what kind of reaction this is. But here we have plus signs on both sides of the reaction equation. That implies a replacement reaction. However, when we start checking the binary thing that I've talked about, here we have something that is binary, something that is not binary, something that is binary, and something that is binary. And with single replacements, we had something not binary, something alone on both sides. With double replacement, everything was binary or higher. With this one here, we have one thing binary on one side and nothing binary on the other side. When you come across this, you say to yourself, oh, maybe this is a replacement reaction of some sort. Maybe it's a combustion reaction. And so the way that we check for combustion reactions is we look for the special reactants that are always there. In a combustion reaction, you almost always have a hydrocarbon. Over here, a compound made up of hydrogens and carbons. Oxygen, something to help the burning along, and then you end up with carbon dioxide and water on the product side. You can't have other oxides over here, but there are always going to be things bonded to oxygen. And so when we see that, we can say, oh yeah, this one is definitely a combustion reaction. And combustion is why I prefer synthesis as my term for this one instead of combination, because it's harder to tell what you're abbreviating, and you end up not being able to abbreviate if you call synthesis reactions combination reactions. But you'll see that some places, so I should at least mention it. Anyway, balancing a reaction, one of the hints, tips, and tricks that I give is that I always save balancing my C's, H's, and O's for last. When I did this one, I started with the H's. Normally I don't, but I have just been reading left to right on all of these examples here. But normally, if I'm actually attacking a problem, I save my C's, H's, and O's for last because I know how balancing works on some more complicated reactions. But here, we only have C's, H's, and O's, so let's just dive right in. So on the reactant side, I have 2 carbons, so I'm going to need a 2 here to give me the carbons balance. I have 6 hydrogens, so I'm going to need a 3 here to give me 6 hydrogens, and oxygens I have 2 over here, and we got to be careful, oxygens in both places here. So we have 2 times 2 plus 3 times the invisible 1. That gives me 4 plus 3, or 7 oxygens. Well, I can't divide 7 by 2 and have a whole number. So you're going to end up with this situation occasionally with combustion reactions. Ideally, we'd love to come in here and just cheat and say, oh, 7 halves, and then we multiply 7 over 2 by 2, we're going to end up with 7, and then we'd be balanced. But we can't balance with fractions, and so the way around that then is to double everything. If I double this one, I end up with 2 there. This one was currently question mark. I had the 7 halves there for a moment, but this one was question mark, double question mark. It's still question mark. We're going to get rid of the 2 there, double it to a 4. We're going to get rid of the 3 here, double it to a 6. And then when we did that, we're going to double all of this math here. If you wanted to write it out again, 4 times 2, that's 8, plus 6 times 1, that's 6. Then 8 plus 6 is 14. But notice that's just the same as doubling the 7 that we came up with. And 14 I can divide by 2, and notice it ends up being that 7 there. And so then there's a combustion reaction that's balanced. In normal reaction equations, you frequently won't get above 6 as your coefficient, and most often no higher than 4. However, with combustion reactions, they can end up really high, and on some of the homework assignments that you do, I have a couple bonus questions on the test. There's a bonus balancing a combustion reaction, and those coefficients get to be gigantic. So have fun taking on those challenges. And so that's how you go about identifying types of reactions and balancing reactions, and you're going to get some practice over these on your own here soon. So be sure if you have any questions that you let me know.